Hi everyone, welcome to the next video. Today we are going to be going over differentiation techniques. So these are the actual ways that you can solve your derivatives. First, I've written down the formal definition of a derivative here. So in the previous video, instead of having an h here, we used the word tiny. So we were denoting it as a really tiny increase along this coordinate to check how much this is changing. And what we were looking for was the rate of change. So we were trying to see how much a function that depends on x changes for every change in the x value. And of course, these variables could change depending on the situation that you're in. So sometimes we want to evaluate a derivative at a specific moment. So we might say we want the derivative of y with respect to x, and we want to evaluate it when x is equal to a. When we say in the domain of f here, we're saying that a has to be somewhere along here. If a is way over here in the middle of nowhere, then it's just not applicable to this problem. So we can denote this with this notation. This could also be denoted as y prime. This could also be denoted as d over dx of f of x, evaluated at x equals a. So you'll see a lot of different notations. Another notation is if you're taking the derivative of something with respect to time. So let's say you have dy over dt. You could also denote this as y dot. The dot is usually there just when it's a derivative with respect to time. And in this case, what would that be? The derivative of y with respect to time in this case would be equal to 0 because our function doesn't change with time. Our function changes with x. So just be careful that you're paying attention to the derivative that you're taking, the variables that you're using when you take your derivatives. So now I'm just going to provide a list of a few different differentiation techniques, and then we'll go through some examples after that. So these are the examples. These are the techniques that you'll need. These techniques will be used right away in dynamics. So you can't do dynamics without using calculus techniques. And so we're going to start off with the basic ones. So the ones in this first series of videos will be the basic ones to get you started in dynamics. And then we'll come back and do a few more complicated techniques later on. So the first one is the power rule. This is the one that we derived in the last video, but this is a better notation for it. So the derivative with respect to x of x to the power n is equal to n x to the power of n minus 1. If you're taking the derivative with respect to x of just x, then that is equal to 1. Then we have trigonometric rules. In this course, I'm just going to ask you to memorize 3 of them. So the derivative of sine is equal to cos. The derivative of cos is equal to negative sine. And the derivative of tan is equal to sec, which of course sec is 1 over tan. There's also exponential and logarithmic rules. So d over dx of the natural log of x is equal to 1 over x, and x has to be bigger than 0 because that's necessary for the natural log to be valid. D over dx of e to the x is equal to just e to the x. This is very, very handy and oftentimes used to make calculations simpler, this property here. And then we'll do one more here. D over dx of a to the x equals a to the x natural log of a. So note here that this is not the power rule because the variable is the exponent. Up here, the variable was not the exponent. The exponent is just a constant number. Now, I should clarify. These rules will get you really, really far, especially in this course, anytime you have simple equations. So you're differentiating one term at a time, and they're relatively simple equations. But oftentimes, you'll end up with equations that are much bigger than that, and you need to have some rules to know how to manipulate those equations before you do the derivatives. So that's what these rules are about. So there's a sum difference rules. This is saying, actually I should clarify this at the top. So we have provided that u and v are differentiable functions, then, and they're together, and you have u plus or minus v, and it's asking you for the derivative. This is equal to the derivative of u plus or minus the derivative of v. The constant multiple rule is if you have a function, so here your function is getting multiplied by a constant k, and then it's asking you for the derivative. That's the same as taking the k out and just taking the derivative of u. So the constants just get multiplied on top of the derivative of the function. Then there's also a product rule. This is uv prime is equal to the derivative of u times v plus the derivative of v times u. So you'll have two, so you started off with just one term of two functions multiplied by each other, and then you have two terms afterwards. The derivative of the first one times the second plus the derivative of the second one times the first. Then you also have the quotient rule. So this is if you have a function divided by another function and it's asking you for the derivative. This is equal to u prime v minus u v prime divided by v squared. And the other one is the chain rule. And this one's a little bit different than these ones here, because this time what's happening is, let's say, in this case you can separate the two functions very easily. U and v are completely separate functions. But sometimes you'll have an equation where you can't separate them nicely into two pieces. And I'll write the formal notation first, and then I'll give you an example. So in this case, you have a function that is a function of another function. So here we have one function inside the other function. If we want the derivative of this whole thing, this will be equal to, we do the derivative of the outside function first, and then we multiply it by the derivative of the inside. So this will look like f prime g of x times g prime of x. So an example of that would be, let's say you have x squared plus 2 square root. In this case, you'll do the derivative of this square root. So you would have, sorry, I'll write this out properly. You have f of x is equal to this. So then d over dx of f of x would be equal to the derivative of the outside. So this means we take the power down, so square root, take the 1/2 down, multiply it by the inside. Don't worry about taking the derivative of the inside to begin with. And then the exponent, subtract by 1, so that's the power rule. So now we've taken the derivative of the outside, and now we multiply it by the derivative of the inside, which will be 2x. And then we could simplify this equation. So these 2's would cancel, so we would end up with x divided by x squared plus 2 square root. This is -1/2, so it's a square root on the denominator. Some more examples of those other rules. Oops, just a sec. So now we'll do some examples. So the first one is f of x is equal to x cubed g of x. So in this case, we have two functions. Do you see how this is two separate functions? We have an x cubed and we have a g of x. In this case, we're given conditions. So we're told that f prime of 2, it's asking for f prime of 2. So find f prime of 2 if g at 2 equals 5 and g prime at 2 equals 1. So here we have the product rule. So this is going to be product rule. So we're going to take the derivative of the first part, so f prime of x, the derivative of this function, will be the derivative of the first term, so 3x squared, times the second term, plus the derivative of the second term, g prime of x, times x cubed. In this case, we don't know what this function g of x is, or what its derivative is. But because we were given initial conditions, that's okay. Now we can evaluate f prime of x is equal to, it's asking us for f prime at 2. So f prime at 2, that means that all of our x's become 2, so now we have 3 times 2 squared, times g at 2, which is 5, plus g prime 2 is 1, times 2 cubed. So then f prime of 2 is equal to 3 times 4 times 5, plus 8 times 1, which is equal to 68. So this function here is the value of the derivative at one moment in time. This function here is the function for the derivative for any value of x. So it's important to understand that distinction because some questions will require you to get the general derivative for any value, and sometimes it's asking you for that value at a specific moment in time.